So we are moving into Unit 5. This module is about probability. We introduced probability throughout Unit 4, but this is a section a little bit more involved probability. Think about questions like if you roll a dice, what are the chances you get something? Our overall course is actually, if you haven't thought about it, it's called Introduction to Probability and Statistics, or maybe Statistics and Probability. And so probability is really one of the large underpinnings of this course, but there are lots of different areas we could focus on. So we've chosen to arrange the material to focus a little less on probability. So if you happen to maybe know some other people in a stats class or seen some other content, we're going to cover a little bit different topics and maybe a little less. We've chosen to focus more on how you use these in how you use statistics in the sciences and kind of like statistical studies, for example, instead of focusing quite as much on probability. So this unit covers two modules, 11 and 12. So this video is only module 11. Module 11 is pretty short in the notes on Canvas in the homework. It's pretty short here in our workbook notes. And then module 12 is not super long, kind of an average length module. And it is very important for down the road. It is in the background of almost all of the probability we learn later. It's what it really allows us to make large answers in statistical studies. So going forward, 12 is really going to be a large focus. 11, we don't directly see too much more of that, so kind of keep that in mind. But with both of those, Unit 5 is not a unit that has a mastery quiz. 11 is kind of its own little topic, something we kind of have to cover, and 12 is something that we need for later, but is not in the background. Like, we really do think about it a lot, but we'll kind of see the final version later. So Unit 5 is not something that has a mastery quiz, and then later, no matter what grade you're going for. And similarly, when we get a little bit down the line, Unit 7 is going to be something similar. It's going to be along the process, and it won't be something we take a mastery quiz on. There is also not a data project for Unit 5, so you just have to choose a data project. When there's not one here, you can see in the table of contents for this unit, there's no data project. So kind of keep that in mind. These are important things to learn, but they won't directly show up later. So kind of think about that balance. Okay, so our first versions of probability, we're going to clarify what some of those words mean. We use the word likelihood and chance in statistics to represent that. Probabilities and percentages are very similar. Percentages can go over 100 though, if you're talking about things going up a percent or down. That's a little different than probability. Probability is very strictly between 0 and 1. And notice that probability there is actually as a decimal. Percentages are totally fine. Feel free to convert to percentage versions. But probabilities are written as a decimal officially. Right, and so in this class we have a lot of different types of probabilities. Something I don't think I've talked about much is statistics and probability are somewhat new mathematically. If you want to think of like a historical old math, you can think of something like calculus. That's been around for a few hundred years. Before that, there were small ideas, and then it really started 300 or 400 years ago. Something like algebra or geometry or trig are much older, hundreds, maybe thousands of years in some cases. Probability is 150 years old, maybe closing in on 200, and statistics came after some of those probability ideas, and some of the ideas are only 100 years old, some a little older than that. So a lot of these are new ideas, and it took people a long time to really decide how these work. So you can't go back, if we had a time machine, you can't go back in time and actually ask people a probability question, even mathematicians at the time, which is kind of interesting. So these are all slightly different types of scenarios for probability. give us an idea of the difficulty and how we think about them now. So you toss a normal coin. What is the probability it lands on heads? The answer is a half. That's not what we're actually asking right now, though, which can we easily estimate. Right? We understand that each side is equally likely, and heads is one of those. There are two sides of a coin. Fair means it, flips. If you flip it, it flips naturally, randomly. It's not like weighted, or it's not a trick coin. That's what that means. So we know that answer. It's a half, and it was easy for us to figure out constructing that one half. Again, actually, historically, that actually took people a long time to realize that makes sense as an answer. We have to be careful. Just because there are two outcomes or any specific number of outcomes doesn't mean we always still know the probability, right? If you buy a simple like lottery type ticket and you're going to win or you're going to lose, doesn't mean it's 50%. It's not 1 out of 2, because the chances of winning and losing, they're not equally likely. So we have to be very careful. Probability is very difficult. Also, one of the reasons we've chose to kind of minimize the discussion of probability here. All right, so another example there, just warming up on these probability ideas. What is the probability that the toss of a bottle cap lands right side up? Can we easily estimate that? No, there's no like mathematical answer we can do. We have to sit there and test it 10,000 times and say, oh, it looks like around 20%, I'm just making that up, it seems to be landing one way. So this one is no. This one is yes, we knew the answer. It's a half, or 0.5. And let's think, just a reminder, LMC is where these notes originally come from. Pretend that's at Crafton. What is the probability a randomly selected Crafton student is female? Now, we don't easily know that, like with probably your knowledge right now, but actually this information is very easy to get if you could list every Crafton student and pick one, which is somewhat similar to going outside of a bookstore or the cafeteria and finding someone. Chances they're female, it's pretty similar. We can figure this out. It's actually public information. I didn't take the time to pull it up, but it's public information. You can go find it. It's on our website. And plus, people who run the different data from Crafton would also easily know that. So lots of people can get this answer. There's a few thousand Crafton students, and roughly, I believe it was recently, 55% are female. So if I go pick one at random, presumably it's about 55%. So yes, maybe we didn't directly know that ahead of time, but it is quite easy to figure it out. So, and these are all much different types of probabilities. So the coin one is very theoretical. The next one is very simulation based. We have to actually test it. And then the last one's kind of in the middle. It's not really a simulation. It is more theoretical, but it really depends on exactly how many females there are and how many total students at campus. Okay, so you'll see some of this in the notes and some different demonstrations. So I'm not going to run through the demonstration here. I have a little applet that I could use. If you'd like to come during Stats Fun Time, I can run through that applet with you. So this is the cumulative probability, so like the long run, seeing what happens, and it's flipping a coin that is biased. And so I think it's checking the chances that it's heads. And so there's like a bunch, each dot represents that there was one more total flip. There's apparently 100 dots there, I guess if we started counting them. And so there's a bunch all in the row. They all stay down at 0, which means there was no heads. So that's a bunch of tails in a row. And then every time it moves a little bit, it switches from heads to tails. And so you can see like long run, somewhere around 20-30-ish%. We don't need to be that accurate. And there's just a website we could use to experiment with this if we felt like it. It's actually random. You can easily ask computers, calculators, to get a random number for you. Excel and Google Sheets very easily do it. You just start typing the word random in the Excel function area, and you get a random number really easily. So This is randomly flipping that coin with some sort of rule, and we're just trying to highlight here the idea of that long run probability. It's like having to flip the bottle cap. We don't know how it's going to work until we actually start trying it. There's a really interesting scenario here. I think I originally saw some examples on TikTok and people talking about it. If you take most shoes, but especially shoes like Converse that are like a really thick rubber bottom and very lightweight, like the material, whatever the canvas material on the top. When you flip that, it'll almost always land, even if it hits and rolls, with the shoe normal ways up, because the bottom is so much heavier. It has like a tendency to roll over and land that way. And so, we could test it. I've only done it 10 or 20 times in a row, and usually 80-90% of the time it lands that way, no matter really how you flip it. But that's simulation, right? There's no like formula or math I could do. If it is, who knows how you would do that to explain why it's going to land that way. It's something we have to do long run. So some probability is done long run. We don't know what it's going to be until we check about it, and it's random along the way. Other probabilities, like coins, we can calculate ahead of time, and we don't have to actually simulate them. So putting that together, when you want to describe the outcomes for probability, we use the word we've been using a lot, distribution, and we call it a probability distribution. And so that just needs to describe all the scenarios for the probability. So the big two categories we have, I use the word theoretical, hopefully that made some sense. Coins and dice, cards, we know how it's supposed to be unless someone's trying to trick you with the cards. Empirical is that idea, I use the word simulation. We have to actually see. We don't know. And so for a coin toss, you have to include all the possible outcomes. So you have a head and a tail, and we know those are equally likely. So that represents one scenario out of two, and so half. But if it's a different coin toss, or maybe it's that shoe or bottle cap we're flipping, it's not going to be equally likely, and we have to test it. Now you can see that you actually just tested it 1,000 times, and you just have a good guess that this is accurate long term for the problem. So empirical is very, very common because a lot of stuff we just don't know why it is, how it works. So for blood type, for example, you've probably heard the most common blood type is O. And before I looked this up, I would have thought that's, what I didn't know is A is very common blood type also. I remember in school AB is uncommon, and I didn't remember really any of the else part, and I knew O was common. I thought it would have been more common based on how much I remember hearing about O. That gets a little bit mixed up with the fact that O is that universal donor, and so if you're familiar with the biology here. So apparently, O and A are actually similar amounts in the 40s. This was actually a large study done, and B and AB are pretty unlikely. So we do have some thoughts about the blood type there. O are called universal donors, right? They can donate to everyone. You can look up the biology if you haven't heard of that, or you've probably heard a little bit about that. So what is the probability if I pick someone at random from the US, they're a universal donor? Apparently, 45% of people have 0.45. Again, percentages to decimals, I'm just going to always naturally do the conversion. 45% of people have type O blood, so if I go and pick someone out, 45% of them, or 0.45. That original study up there was done with 50,000 people. And how many actually had type O blood, right? So what does 45% mean there? If I multiply and take 45% of 500,000, I'll figure out how much there actually was there. So that'd be 225,000, multiplying 0.45 times 500. So in the 5 study, that's how many people there were. Right, so most of our calculations here are formed by fractions. Gets us most of our probabilities for right now. So in general, if you're describing a proper true probability, then there is some patterns there. Any probability has to be between 0 and 1. 0 would mean it's impossible. 1 means it happens all the time. What is the probability the sun rises tomorrow? Maybe we don't see the sun. Maybe we have a bad streak of weather, but chances that the sun rises or the earth turns, right, 100%. And you could think of something impossible. I don't know. Now, a proper probability distribution, so these are all the outcomes of what your blood type could be, not including the other characteristics of blood type, like plus minus. In the simpler categories, what should happen if we have a proper probability distribution? These should be all the categories, which means they should add to 100% or 1 when you add them all up. So it's 1 or 100%. So those are some small things to think about for probability distributions. Dice are something, there's 6 sides of a dice, like a box has 6 sides. Roll a dice, you expect each one to be equally likely. But if you do something like count, some random study here, counting how many eggs in an owl nest, if you count how many cars people have or kids people have, then you just need to actually go and do it empirically. This is what they found for their study. I'm going to kind of skip some of these small questions here. Relative frequency is just another way to describe probability. So the word relative just means probability. Oops. And so you want to use probability to describe your answers. And so frequency means how many, it means count. But then you divide it by the total to form relative. They are almost always going to be done as decimals, so technically probability and not percentages. So this is a little bit old now, but this is the amount of 3-point shots from Steph Curry over the season. It's how many 3-point shots he made per in an individual game. So 1% of the time he made 9 3-pointers, and all the other ones with me. So it's a histogram. We could have done it with actual counts, but this gives us some extra information in case that's more helpful. This is the normal mean and standard deviation. So that's just the mean and standard deviation from the original data. Small comment about that. We really wanted you to consider thinking about the median, the IQR, and the box plot a lot more. But it does turn out we're going to really focus on the mean, right? And when you use the mean, you have to use the standard deviation because those are the ones built with each other, right? The standard deviation is the average distance from the mean. And so you'll see from now on in the class, we really focus on the mean and the standard deviation to measure the center and the spread. We said if our data is skewed, we don't really like to use it, but essentially we just kind of hope that our data is not that skewed. So this is practically what we usually end up doing. Okay, so is it unusual for Steph Curry to not score a 3-point shot? Right, what would that mean? That would mean 0 3-pointers. It's only 1%, so yes, it definitely seems unusual. I think there's an extra U in there. Unusual. Only 1% of the time. Right, 0.01 is 1%. So we're going to continue in the class and end up describing how do I know if something's unusual. Like 1% is, I think everyone agrees that's not very likely. 30% chance is kind of likely. It's not super unusual. If something happens 30% of the time. 5-10%, we would have a hard time probably deciding if we know if that's a cutoff. So from now on in our class, we're often going to cut off right around 5%. If something is less than 5%, it's fair to call it unusual. And if something is greater than 5%, most of the time we're going to call it not usual. Be careful about that, but it's not unusual. We'll try and talk about that more, and that'll come up a little bit in Module 12 also. Um, okay, so we've mentioned this before um, I think, back in Module 7, I think. So a typical interval, one nice thing about the median and the IQR is that they give you a really good quartile 1 to quartile 3, really short and quick. But like I said, long term, we don't actually use median and quartiles quite as much. There's mathematically some big disadvantages in those. So we more frequently use the mean and the standard deviation. And so this within is when we did the mean plus and minus 1 standard deviation. So right now that'd be the 4.1 rounding plus and minus 2. So 4 plus and minus 2, 4.1. So 2.1 up through 6.1. Especially mine is color-coded. You might notice that that was already marked. That's what these red bars are here. That's an option in StatCrunch to mark 1 standard deviation each way. And the point is that it captures a lot of the data. And it captures kind of the most important middle of the data. The center is one of our focuses of the big 3 and what we describe data with. What is the probability that he hits this amount of 3-pointers in a game? Now, it's a little bit up to us interpreting. So it goes from 2.1, like visually that line right here is hitting the box for 2, but we know that these numbers are whole numbers. So there's kind of an issue between what the graph is showing us and what that actually means in the data. If you went from 2.1 to 6.1, you actually probably shouldn't get the 2s, but visually it's including them. That's just an issue of how graphs can oversimplify some stuff sometimes. I wouldn't really mind either way which one you calculate. They're both reasonable. So let me clean this up. So we want to calculate probability of landing between, let's just go from 2 to 6. We'll include the 2. So all of these probabilities here. This is just a random real-life data set. It's a little bit skewed right, it's skewed right, which probably we would expect, because every now and then you have a game where it goes really well and you score a few extra than normal, because there's a minimum of 0. A lot of times when there's a minimum value in something, you get data that looks a little bit skewed right. So what are all those probabilities? So 0.1, 0.25, 0.18, 0.17, and 0.08. And if we add them all up, we find the overall probability of getting within 1 standard deviation, which we could call a typical interval. So I'm going to go and add those up. So that was 78%. And so that was a large percentage, right? Most of the time, 78% is really high. Most of the time, he's going to score with in that many. All right, so our typical interval, we're actually going to be able to describe that a little more if you have very specific data, like we will in Module 12. Module 12 focuses on a very specific type of data. We can actually make this typical interval thing even more concrete. So that'll be something for there. And lastly, we have one small last topic here. This is it's its own probability topic. It's also something we've exactly done before, and it's also something we've slightly done before. A lot of these topics overlap. But in general, this topic called expected value is what allows you to if you wanted to think about this more, how to determine is playing a lottery game worth it. And so if you look on lottery stuff, they often tell you the odds, but a more common way for probability and mathematicians and statisticians to think about that is to think about the idea of an expected value. And so in the long run, you can use that to answer something like, okay, if the game costs me $2 to play, most of the time, what do I expect to win back? In real life, you either win nothing, or you win $2 or $10 or $1 million or whatever. But it'd be on average, if I play a game for $2, I might expect to win like $1.10 back, right? I mean, gambling normally loses money, right? That's why the games exist. And so that could be described as the expected value. Or, if what did I say, losing like $1.10 or $1.20, getting back $1.10. So it's kind of like every time you're just giving 80 cents. But of course, in real life, we know every now and then randomly you win a lot, but this is thinking of like a long run value. Okay, so this is also very similar to the weighted mean. That topic was in the notes. I don't think it even came up in like the any checkpoints. It wasn't on any of the mastery quizzes. It's a very specific thing, but this is also almost the exact concept as the weighted mean. Okay, so I'll go through an example really quick here. So back to basketball. How many three-pointers, but it's a high school student now. So there's 25 games. So you see all the zeros, ones, twos, and times he scored 3 three-pointers. So these are games where they didn't score a single three-pointer. They scored 1, 2, and 3. All right, summarized. So there's 8 times they scored 0. And then you have all of the different probabilities there. So there were 25 games total. So like, how did we get to 32%? That would have been 8 out of 25 would be 32%. I'm going to double check. 32%. All right, I mean, the graph there is from StatCrunch, so we should trust it. This is the exact same data. So, 3 different visuals of the exact same data here. So 9 out of 25, that's the 36% you can see there. 0.36 is the probability. Again, I'm going to naturally go back and forth between each one. 6 out of 25 is 24%. And 2 out of 25 is 8%, 0.08. Okay, so expected value is just the same idea as the average. And sometimes in probability terminology, you don't have access to the original data, like up here. And like with a coin, if it's theoretical, I don't have this data, so how do we calculate an expected value? I don't want to have to play the lottery 1,000 times before I can understand the expected value. So there is a way to figure out the expected value. This is not something you're going to be tested on. This is not a unit that has a mastery quiz. I'm pretty sure the unit checkpoint on Canvas also doesn't have this question. So this is kind of for informational purposes only. Feel free to stop the video here. So the expected value, often represented EV, is mathematically, you take all the values and multiply by their probabilities. And then, sorry, I didn't say it when I first wrote it down, we have the sigma, we add up that procedure. So you add up all of the values times their probability. So you do the value, so you had 0, there was a lot of zeros in the list, so think 0 is the value times the probability, which was 0.32. That's going to be 0 no matter what, but this is the procedure. You take the values times their probabilities and add those all up. So 1 times the next value, and its probability is 0.36. 2 times 0.24, and then 3 times 0.08. We could put this whole thing into a calculator. That one's going to go to 0. You could do this slower, 0.36, 0.48, and 0.24. So we add all of these up, and this is the expected value. It's identical to the idea of average. If your data makes sense, it is exactly the same thing as average. Sometimes for coins and games and stuff, it makes a little more sense to call it something different. So the expected value is 1.08. So how many three-pointers is this person expected to make in a game? 1.08. right? So a little more than 1 is another way to think about that. Most of the time, this person makes a little more than 1 3-pointer, but not all the way to 2. So that is the way to interpret this. It's identical to the idea of average. Right, I believe that finishes off. Yep, that finishes off Module 11 in Unit 5. And next we're going to switch up the type of data we choose to understand. So I will see you in Module 12.